We are going to present a wearable device for monitoring bradycardia. We are Eliana Patarroyo and Nicolas Zúñiga. This is our table of contents.
Bradycardia is a condition where the heart beats slower than normal, commonly below 60 beats per minute, as determined by an electrocardiogram. Bradycardia can be a symptom of various conditions, including heart disease, electrolyte imbalances, medication side effects, thyroid disorders, and other cardiac abnormalities. Detecting bradycardia early can be crucial in identifying these underlying conditions and initiating an appropriate treatment. If this disease is left undiagnosed or untreated, bradycardia can lead to complications such as fainting, dizziness, shortness of breath, chest pain, and even life-threatening events like cardiac arrest or sudden death. Monitoring the heart rate is necessary to detect abnormal heart rhythms, determine the severity of the condition, prevent complications, adjust medication, and optimize exercise routine and overall improve health.
The proposal is based on developing a wearable device that allows remote monitoring of heart rate for people predisposed to experiencing arrhythmias, specifically bradycardia, with the aim of preventing consequences such as fainting or, in more severe cases, sudden death.
For wearable device, we will define three main objectives. The first one will be the appropriate signal amplification. The cardiac signal is of low amplitude, so the circuit needs to have an amplification stage that effectively increases the signal to a usable level without introducing distortion or additional noise. The second one will be the optimal signal filtering. It is necessary to apply filters to remove unwanted noise and electromagnetic interference that may affect the cardiac signal. Low-pass filters should be used to eliminate non-relevant frequencies while preserving the frequencies of interest associated with cardiac activity. The third and the last one will be the user interface and notifications. This circuit may include a user interface that allows real-time monitoring of heart rate and provides notifications in case of bradycardia detection. Now for our functional design, we will define a belt as our wearable. In this belt, we will place our circuit and we'll connect it to our body through two connection cables, which will have two electrodes in the extreme of them. This circuit will be powered with the help of a 9-volt battery and will be connected to our Streamlit interface to show the ECG signal in real time.
The process begins with the placement of electrodes on the patient's body. In this way, the electrodes, which are sensors, will capture the electrical signal of the heart and acquire the data. After that, amplification follows as the heart beats and low-frequency signals around 60 Hz. Therefore, it is necessary to amplify them to improve the amplitude and make it easier to process and analyze. Next is filtering, which involves removing unwanted noise from nearby devices like a cell phone, among others, or even signals from the body that do not correspond to the heart. In this case, we will apply both low-pass and high-pass filters, and then comes digitalization, which allows storing the data on a computer and manipulating it. After that, digital manipulation is performed to specifically acquire the required data, such as the peaks. Finally, visualization is done to display the result. The circuit has two essential sections. First is acquisition and amplification stage. In this section, signals enter the instrumentation amplifier INA, which allows them to have the desired gain for small or low level signals. The amplifier is powered by 9 volts and -9 volt sources. The positive input signal at pin 3 was generated with an Elvis, while the negative input signal was connected to ground on the same Elvis. Second, we have a filtering stage, and this stage consists of two second-order active filters. The first filter connected to the INA is a high-pass filter that attenuates low-frequency components. It includes two capacitors 7 resistors, and an operational amplifier. Following with that is low-pass filter, which attenuates high frequencies and allows low frequency to pass. For this filter, we have two capacitors, 4 resistors, and another op-amp. This is our data diagram. This diagram represents a basic implementation of real-time acquisition and processing of ECG data. First, we have digital sign. We use a function that is responsible for acquiring ECG data. It establishes a connection to a remote server using a specific IP address and port this. So we have these values and converted these to float type and added to the variables called bdatos and btiempo. Finally, this is stored in a signal and corresponding time. After that, we have digital processing. In this case, our function handles the processing of the ECG, whereas process only a portion of the most recent data to be more quickly, and next searches the peaks with a function called find peaks. After that, we have the key features of the ECG. In this part, we calculate the our peaks, dividing the difference between the peaks by the sampling frequency. Additionally, we use a library called biospeed to calculate the heart rate. Finally, we have the visualization. In this part, we use use a code that figure two subplots with an infinite loop. These graphs are updated with the most recent data. The first graphic is the signal of the ECG, and the second graphic is a tachogram. In this video, you can observe the result of the implementation of the circuit along with the algorithm performed. And now for this video, we have the implementation of the web page. It shows a header with information about the disease, a representative image of the wearable device, and then the electrocardiogram signal with the marking of the RPs. Below this graph, the tachogram is displayed, and it is worth noting that there are limitations of these application are that it has issues with the displaying real-time signal with a slow update rate. Additionally, the signal acquisition process is flawed, resulting in it scattered. And now for this video.
Now for our conclusions, we will define two main conclusions. The first one will be that the implemented circuit successfully amplifies the low amplitude cardiac signal to a level suitable for further processing and analysis. And the second one is that the integrated user interface in the wearable device provides a real-time monitoring of the heart rate and timely notifications in case of bradycardia detections. This empowers users to stay informed about their cardiac health and take necessary actions or seek medical attention promptly when bradycardia episodes occur. The user-friendly interface enhances the usability and practicality of the wearable device for